Everybody, it's a great pleasure to welcome you all here to the Royal Astronomical Society, who are kindly hosting our workshop on fine-tuning in quantum and cosmological scales. We have what I hope is a really sort of exciting program for the day. It's a pretty tightly packed program, so if I can ask everyone to sort of try and really respect the calendar, the clock, in terms of our schedule, otherwise we're going to overrun and people are going to run out of time for their talks. The speakers should all leave roughly 5 minutes for questions at the end, but when we do have questions, because we are recording this, can you wait till, put your hand in the air and wait till you're handed a microphone before asking your question? The microphones are not being amplified, nothing is being amplified, this is just for the purposes of recording things so we get a proper full record of what people have said. Everybody happy? Okay, so...
Do I need a microphone?
No, you don't. These things will pick you up. So without anything further, I'll hand over to Raphael, who's going to chair our first session and get things underway.
Yes. So I should just advise you that we'll have 1 minute of silence due to Armistice Day around 11, right after Bernard's talk. Okay. And now we can get started.
Never my talk, so I will.
Well, it's after your talk. Yeah.
Well, I should stop at the.
Okay,
If you prefer to stop.
11 minutes past 11. Is it actually 11?
11 o'clock.
So we can stop at 11.
Well, I think I should stop at 11. Yeah.
Very well.
Okay.
As long as I don't have to end my talk.
Okay, so we stop at 11 o'clock for 1 minute of silence for those of you who wish. And now I hand over to Bernard Carr from the Queen Mary University of London. We'll be talking about fine-tuning and the Big Bang, linking microphysics and microphysics.
Thank you. So my job is to introduce the day. And as I say, I'm going to introduce the concept of fine-tuning and stress in particular its link to the Big Bang and relationship between microphysics and macrophysics. And I want to start off with my favorite diagram, which is called the cosmic uroboros. It's the snake which is swallowing its own tail. And around the body of the snake are all the scales of structure which exist in the universe. So at the bottom we have people, and then as you go to the right, you have increasingly large things, mountains, planets, stars, galaxies, the universe. As you go to the left, you have increasingly smaller things. So you have ants and amoebas and DNA and cells and atoms and all sorts of particle physics, things we don't know much about. And of course, the aim of physics is to try and explain all those structures, and the triumph of physics is that it has actually succeeded. So on the left, we have the microphysical domain, and on the right, we have the macrophysical domain. And basically, the universe is very simple at the smallest and largest scales. It's most interesting in the intermediate regime, the mesophysics scale, which is where human beings in complex structures arise. And so to understand this diagram, you should think of the body of the snake as a sort of ruler in which the scale increases by a factor of 10 for every minute as you go around the clock. So there's something like 60 decades of scale as you go from the scale of the universe at roughly 10 to the 27 centimeters to the Planck scale, which is 10 to the minus 33 centimeters. Now, the other important feature which has come out of physics is that the forces link the microscopic and the macroscopic domain. For example, the electric force which holds the electron in orbit around the proton is the same force which determines the structure of solids. The weak and the strong forces which hold nuclei together are also the forces responsible for the generation of energy through the burning in stars. The electroweak force, which is associated with the electroweak unification, is probably associated with dark matter in some way. And the grand-unified theory, the unification of the weak, electric, and strong, in some sense relates maybe to the inflation in the early universe and the generation of density perturbations. And so those forces are what provide the link between the microphysical and the macrophysical domains. And in some sense, the history of physics can be thought of as the history of the unification of forces. So electricity and magnetism were unified in the electromagnetic theory. Weak force was then unified with the electroweak theory. And then the strong force, which is still not being experimentally verified, is unified with grand unification. And of course, the great aim is to unify that with gravity, and our current candidate is M theory. And so it is the great triumph of physics, in some sense, to produce this wonderful understanding of the physical universe on this huge range of scales. Now, of course, what's really interesting about this is that the head swallows the tail at the Big Bang. And so in some sense, the Big Bang you might think of as the culmination of this link between the macro and the micro domains. Why does it bite its own tail at the Big Bang? And I think you will understand that because in the Big Bang picture, the universe began about 14 billion years ago. When you look to great distances, you're looking back in time. So when you look back to something like 14 billion years, you're looking back to when the universe was very small. So in some sense, the very large merges with the very small. And if you want that in a slightly more technical way, this is a diagram that shows how the backward light cone converges at the horizon. And so in some sense, the fact that it converges back to the point there is equivalent to the top of the uroboros. Now, since we have a talk later in the day about George Lemaitre, I should, of course, mention the fact that the father of the Big Bang was indeed George Lemaitre, who in 1932 proposed the primeval atom model of the universe because he realized the expansion of the universe implied it started in a very compressed state. And so he already, by talking about the primeval atom, had realized this important link between cosmology and particle physics, between microphysics and microphysics. And I will just advertise the talk by Simon Mitten, which is this afternoon. Simon is talking today because today, or at least roughly today, I believe, is the 50th anniversary of his death. So you'll hear more about that later. Of course, nowadays, we know a lot about the history of the universe from the Big Bang through various stages, all the way to the formation of galaxies and eventually the formation of human beings, as depicted by this eye. I'm not going to go into the details of the Big Bang theory. I think you probably all know the rough picture, so I will just assume that is known. But the important point is that this Big Bang, which is at the top of that cosmic uroboros, it represents, in some sense, the culmination, the link between the ultimate microscopic domain, which is something to do with the vacuum, the smaller scales of nature on the left, and the macroscopic domain of galaxies on the right. And we know also that the microscopic domain is the realm of quantum theory, and the macroscopic domain is the realm of relativity theory. And roughly speaking, the structure of the day is we're going to talk about the large-scale things in the morning and the small-scale things in the afternoon. So if we go back to this picture, which I gave before, not only does this represent the Big Bang at the top, it also, in some sense, will represent whatever our final theory of physics is. That final theory, which is going to marry relativity and quantum theory, sits there at the top. And our favored theories, of course, at the moment, involve rather odd concepts like M theory on the left, our theory of the very small and the multiverse on the right, our theory of the very large. Of course, these are controversial concepts, but the point is you inevitably are going to confront these controversial concepts when you get to that top of the uroboros. And I will mention this controversy by reminding you of a paper which came out recently by George Ellis and Joe Silk about the fact that M theory and the multiverse raise fundamental issues about the nature of science, because you're dealing with concepts which may underlie reality, but which are very hard to test. So there's a very a valid question to be asked about what is the nature of science. What is the border between, if you like, physics and metaphysics? I don't want to get into that. I have my own views. I don't completely agree with George and Joe, but I do agree that it's a very important question, and I think one has to address that question. And it's particularly relevant when you come to talk about the anthropic principle and the fine-tunings. Well, let me just, in introducing the anthropic principle, I want to make a few distinctions. We have to distinguish between the anthropocentric view, which says that man, when I say man, of course, I mean humans, but man is the central to the universe, and of course, that lost that view a long time ago. And then with Newton, we got the mechanistic view, which basically says the universe is like a giant machine and is really operating independently of whether anybody's observing it. So from that point of view, I should say humans when I say man, sorry about that, and mind are irrelevant. And so that's my image of the mechanistic Newtonian universe. But then the anthropic view, which arose about 50 years ago, says that some features of the universe do seem to be explained in some sense by the requirement that life and mind should arise. And that's called the anthropic view because anthropos is the Greek word for man. It's a terrible, and there is the image with the eye in the center, implying that the observer plays some important role. Actually, it's a terrible term because it's really nothing to do with human beings. From my mind, at least, it's more to do with complexity. The universe seems to be designed so complexity can arise. And you can see the history of the Big Bang as being a process of increasing order, if you like, which culminates in brains and mind. Now, the subject has a long history, and my introduction to it was in 1979 when I wrote a review paper with Martin Rees, The Anthropic Principle and the Structure of the Physical World. And it's now quite a well-known paper. It was one of the first reviews and expositions of the topic, but it was very controversial. A lot of people were annoyed because they thought it was really not proper science, and but now it's almost respectable. So 40 years makes a lot of difference. But the first thing I want to stress is that there are many different types of tuning, and this day is about tuning, and I think it might be useful to distinguish between these different types of tunings. Now, the first point to make is that, and one of the points I made in the paper with Martin, is that physics implies natural coincidences between the different scales of structure in the universe. And there's nothing metaphysical about that. It's straightforward physics. And a very simple example, the human being, our size is roughly the geometric mean of the Planck scale and the size of the universe. And you might think, well, that's a bit weird. It's not weird at all. It's predicted. And I'll just give you a few simple examples. I can take many mass and length scales, like the size of the universe, stars, humans, proton, and the Planck scale, and I can express them in terms of physical quantities like the proton mass, the size of the atom, the fine structure constant alpha, 1 over 137, and the gravitational fine structure constant, which is about 5 times 10 to the minus 39. And these are predictions which come out of straightforward physics. And that in particular, you can just look at that and you can see that it implies the size of a human being is a geometric mean of the Planck scale and the size of the observable universe. So straightforward physics, that's not controversial at all. There's another type of effect, and this is what's called the weak anthropic principle. And it says that there is a selection effect for when and where observers exist. And the famous example of this is the Dickey coincidence about the age of the universe. You might ask the question, why is the universe as huge as it is? Well, we know that the universe began with a Big Bang 14 billion years ago, so its size is roughly 14 billion light years. So you might ask, why is that the case? Well, the mechanistic view says the size of the observable universe just happens to be roughly 10 to the 10th light years, 14 billion light years to be more precise, but there's no particular reason for this. On the other hand, Bob Dickey gave another answer. He said, life requires heavy elements. Those have to be made in stars, and then those stars explode and disseminate the elements through the universe. But it takes a certain time for stars to go through their evolution, which is roughly 10 to the 10th years. And so basically, there wouldn't be any elements before 10 to the 10th years. On the other hand, if you waited much longer than 10 to the 10th years, all the stars would have burnt out, so there wouldn't be life either. So in some sense, it's saying that life is only going to exist when the age of the universe is roughly 10 to the 10th years and its size is roughly 10 to the 10th light years. So in some sense, this explains why the age of the universe is 10 to the 10th years. It also relates it to the value of alpha g. In fact, it's alpha g to the minus 1 times the proton timescale, again from simple physics. So this isn't saying the universe doesn't exist. outside 10 to the 10th years. It's saying we would only be around asking questions about it. And really, I regard this as essentially uncontroversial. It's simple logic that the presence of observers imposes a selection effect on when and indeed where we exist. We have to exist near a star. So I personally regard that as completely uncontroversial. But then the more controversial aspect is what's called the strong anthropic principle. And this says that the constants of physics themselves seem to manifest certain fine-tunings, which are not predicted by physics, but which seem to be required for observers. And so that's what I want to focus on mainly. Well, what do we mean by constants of physics? I've listed a whole lot of fundamental constants there. You don't need to read them all. But one of the first issues is which constants are actually fundamental, because any final theory is going to relate the constants of physics in some ways. But so we don't know which are the fundamental constants. Presumably there's some very small subset. And then the question is which of them are going to be independent. But normally we want to focus on numbers which are dimensionless. And the most important dimensionless numbers are associated with the forces of nature. And these are what are called the coupling constants. So the strong force has got a value, they're all denoted by alpha of about 10. The electric force is about 10 to the minus 2. That was the famous number 1 over 137. The weak force is 10 to the minus 10, and the gravitational force is 10 to the minus 40, roughly. And the question is, will our final theory actually explain what those values are? Obviously, most physicists would like to think they will be explained. Now, there are, though, certain relationships between those constants which seem to be necessary for us to be here. And let me give you a very simple example. The stars, all stars have a mass of something like alpha g to the minus 3/2 times the proton mass. Again, simple physics. Remember, alpha g is 10 to the minus 42, so you can confirm that's correct. But there's another subtlety, is that there are two different types of stars. There are stars where most of the energy is getting out through radiative processes, and stars where it comes out through convective processes. And we need both types of stars because the convective stars are the ones which seem to be associated with planets for some reasons, and the radiative ones are the ones which are associated with supernova. And the transition between those occurs at alpha g to the minus 2 times alpha to the power 10 times the proton mass. So the only reason that both types of stars exist is because of this remarkable coincidence that alpha g is the 20th power of alpha e. Now, it's clearly true because if I take the 20th power of 10 to the minus 2, I get 10 to the minus 40. But the point is, this relationship is required for life, but completely unexplained by physics. This is my favorite coincidence, simply because it involves such a high power of alpha. More recently, it's been examined by Page, and it's satisfied to something like 3%. Now, if I go back to my uroboros diagram, that's rather interesting, because if I write down what the scale of these various objects is, it just depends upon alpha g to various powers. So we have the size of the universe is alpha g to the minus 3/2, human beings alpha g to the minus 3/4, and the Planck scale is 1. So this is in units of the Planck scale. But the question is, what actually determines the scales is the value of alpha g. And the reason there's 60 decades of scale is because alpha g is 10 to the minus 40. If alpha g had a different value, the same diagram would apply, but it just wouldn't be 60 decades. Here's another coincidence. This involves a relationship between alpha g and the weak force. And for supernova explosions, alpha g has to be the 4th power of alpha w. And the reason is this, roughly speaking, when a star collapses after nuclear burning, it generates a lot of neutrinos, and the neutrinos are what blow off the envelope. If the weak force was too weak, they would just stream through and not do anything. If it was too strong, they would get trapped in the core. The only reason they can blow the envelope up is because of this fine-tuning. Now, again, that's true that the 4th power of 10 to the minus 10 is 10 to the minus 40, but it's not explained. And oddly enough, the same coincidence explains why you get interesting amounts of helium in the Big Bang, and it even explains why baryonic and dark matter densities are comparable. So that's, again, quite a fundamental relationship. But the point is, this relationship is required for life, but unexplained by physics. Here's another famous one. This is the triple alpha coincidence, which Fred Hoyle worked on in 1953. Life requires carbon, and of course, I'm talking about the sort of life we are. And carbon is made in stars through triple alpha, and it's a two-stage process. First of all, two alpha particles make beryllium nuclei, and then the beryllium nuclei interacts with another alpha to make carbon. But actually, the only reason this, normally speaking, beryllium would decay too soon for the second interaction to go ahead, but there is a fine-tuned resonance which allows it to happen. And in fact, a more recent calculation shows that the strong interaction has to be tuned to something like 0.1%. And what's interesting about this, it was actually a prediction. Fred Hoyle said to his friend Willie Fowler at Kellogg in Caltech, he said, look, there has to be a resonance, look for it, and they looked for it and they found it. So that's quite exciting. Now, I have to say that, because people often say that all the anthropic arguments are retrospective, I have to say that it's not quite as simple as this. Fred Adams has written a series of papers where he says stars in other universes are not rare, as sometimes claimed, and he's got a parameter fit for alpha G over alpha. You can't really read it, but he's just showing there's quite a wide range of values for which you might have stars. So it may be that the argument I presented is a little bit simplistic. I'm not going to go through the details, but these are some of the calculations he's done, and they're the papers. I'm just showing you the graphs to indicate that people have looked at this in rather carefully. But then there are a lot of constraints from chemistry. For example, if alpha S was increased by 2%, all the protons would go into diprotons at Big Bang nucleosynthesis. There wouldn't then be no hydrogen-burning stars, and there wouldn't be time for life to arise, because a helium-burning star has a much shorter lifetime. If it was increased by 10%, all the protons would go into nuclei of unlimited size, and there would be no interest in chemistry. If it was decreased by 5%, the deuterons will be unbound, and you'd only have hydrogen, and then again, you wouldn't have interest in chemistry. And so there are constraints involving the mass, the relationship between the electron and the proton mass, the difference between the neutron and proton mass. And so this diagram on the right shows, that's the diagram with alpha S, the strong coupling constant against alpha. There's only a very small range, which is basically the white region in the bottom left-hand corner, where you can be if you want to have an interest in chemistry. Nowadays, we can also relate that to the nature of quark masses and the QCD strength, but I won't go into that detail. But then there are also a whole lot of coincidences which are associated with cosmological numbers, and these have been discussed in Martin Rees's book, Just 6 Numbers. The first two I've already talked about. The third one is the density parameter. The fourth one is the cosmological constant. The fifth one is the amplitude of the density fluctuations, and there's even the number of spatial dimensions. I'll go through these quickly because I think you're probably fairly familiar with the arguments. We know that the density parameter is going to determine whether the universe recollapses or expands forever. If it was much larger than 1, the universe would collapse too quickly. If it was much less than 1, fluctuations would never freeze out. So we knew a long time ago, even at the time I did my review with Martin Rees, that omega had to be between about 0.1 and 10. And nowadays, of course, we know that inflation predicts omega equals 1 with great precision. So some of these arguments eventually get superseded by more respectable physical arguments rather than just anthropic arguments. We would all prefer a nice physical argument to an anthropic argument if we could get away with it. And this is an example of something where, in some sense, we don't need to invoke, apparently, an anthropic argument. On the other hand, even inflation requires fine-tuning. And I don't want to go into the details of inflation, but let me just briefly say that, most cosmologists seem to believe in inflation, But the point, and there's huge numbers of models of inflation, but I think of it more as an effect than a cause in some sense. And although it's true that there are many predictions of inflation, scaling invariance of fluctuations, Gaussianity, things like that, other theories could also predict that. So I think it's circumstantial evidence in some sense. If you took a vote, if you took a census of all cosmologists, probably most would believe in inflation, but, well, it's like, remember what happened with Trump, where the predictions were wrong. Yeah. Inflation, it has to start, it's got to last long enough, it's got to end in the right way, it's got to make the right density fluctuations. What is the inflaton? You're dealing with sub-Planckian scales initially. And Carroll and Tam actually once argued that inflation was fine-tuned to 10 to the minus 10 to the 7th. I don't want to get into that dilemma, but in fact, inflation, as you'll see, does link up with one's attitude towards the multiverse. There are also constraints on the photon to baryon ratio. This is a bit technical. I'll just go over it quickly. The photon to baryon ratio is about 10 to the 9th. You might say, why does S have that value? Well, if you want the universe to be matter-dominated at the Dicke time, S must be less than 10 to the 10th. If you want it to be radiation-dominated at Big Bang nucleosynthesis, it must be bigger than 10 to the 4th. Nowadays, we think that the value of S reflects the baryon asymmetry before the quark-hadron phase transition, but even that depends on parameters. The baryon asymmetry tends to depend on the unification coupling constant to some power in simple models, and so that also gives you a coincidence, which oddly enough is rather similar to the convective star one if n was 5. And then there's the amplitude of the fluctuations, which is the amplitude measured by the CMB, roughly 10 to the minus 5. If it was less than 10 to the minus 6, gas wouldn't collapse into gravitational bound structures. There would be no galaxies. If it was bigger than 10 to the minus 3, everything would go into black holes rather than stars. This is a rather cluttered diagram, but it sort of summarizes all the results. And there are various physical conditions. Here's a rather complicated formula. This is the most complicated one I'll give you. It's just saying these are constraints on Q, which comes from various arguments, which I'm only sketching briefly. You can do the same thing in the cosmological, with the cosmological constant. But the point is, again, it's in that white region with the little star. That's where we actually are. Now, we don't know what the value of Q is a priori, but we know it has to be constrained in this way if you want galaxies. Then the most famous one of all is the cosmological constant. We know the universe is accelerating. We know that there's this famous 120 orders of magnitude discrepancy between the observed cosmological constant and the most natural one, which is in some sense the Planck scale, well, 1 over the Planck scale squared. It was Weinberg who pointed out that, and so the question is, if lambda isn't 0, for a long time people thought it was, if lambda isn't 0, how come it's so small? And Weinberg pointed out that if omega was lambda was less than 0.6, that you couldn't have galaxies. And that was actually an anthropic prediction. He made that prediction before they actually measured the acceleration of the universe. It was way back in 1987. And you can also constrain the combination of lambda and Q. This is quite a well-known diagram. I talked about Q before. Well, you can constrain the combination. Linda and Vastrin have even said the anthropic principle is the only known solution to the cosmological constant problem. That's too strong. I don't think you can say it's as strong as that, but at least it is a view. That's why I've got lots of question marks. And I know Francesca is going to talk about this question afterwards, so you'll hear about this in much greater depth then. So let me just summarize. I'm going to stop at 1 o'clock. I never stopped in the middle of a talk before, but I'm going to stop at 11 o'clock for the 1-minute silence. So let me just summarize these fine-tunings. Those are all the fine-tunings I've talked about, and I won't go through them all again. I just want to get across to you that there are a lot of these fine-tunings. And ultimately, your attitude to these anthropic fine-tunings, whether you think they're interesting, depends on how many they are and how precisely they are satisfied. I'm going to, this is the let me just say, this is the anthropic constraints on the number of space and time dimensions, but I'm not going to go into that. And the final one I'll end up is there are non-anthropic fine-tunings, which aren't directly related to life, and one of those is related to the Higgs mass. We know the Higgs mass is 125 GeV. Another interesting coincidence, that's the geometric mean of the energy associated, the energy scale associated with the dark energy and the Planck mass. Don't know why it should be that, but the more important point I'm trying to make is that several people have pointed out that our universe, that there is a strange tuning involving the Higgs mass. It's where that black dot is. And the universe would be unstable if it was a slightly bigger. And we still don't understand what causes that fine-tuning. But that's not an anthropic fine-tuning. It's a different sort of fine-tuning. So what I want to do now, it's 11 o'clock, so can I ask the chairman to tell us when 1 minute is over?
Have a minute's silence.
Thank you.
Could you go back one slide?
No, I'm sorry, I won't. I'll not get to the end of my talk. I'll do it at the end.
Okay.
So, first of all, I would say it seems interesting we're having the 1 minute silence to remember a very human event, because in some sense that's what the anthropic principle is about, is asking, is there a place for humans in science? And in some sense it's interesting we've had this moment to think about humans in a scientific talk. Now, let me return to the anthropic principle. What's the reaction of people been to this? Historically, it's been very different. Freeman Dyson, I do not feel like an alien in this universe. The more I examine the universe and examine the details of its architecture, the more evidence I find that the universe, in some sense, must have known we were coming. He's always been a great supporter. But Hans Peijel, the influence of the anthropic principle on contemporary cosmological models has been sterile. It has explained nothing, and it has even had a negative influence. I would opt for rejecting the anthropic principle as needless clutter in the conceptual repertoire of science. Strongly against. An anti-view, Brandon Carter, the anthropic principle is the middle ground between the primitive anthropocentrism of the pre-Copernican age and the equally unjustifiable antithesis that no place or time in the universe can be privileged in any way. I would say that that is the balanced view, and of course Carter was the person who introduced the word anthropic. Now, one of the issues is, though, what actually are we selecting for? I've explained that the word anthropos means man, but of course it's nothing specific to us. You could argue, is an observer a human being, a mouse, a robot, a photon? Professor of mathematics, it's really completely unclear. So that's one of the criticisms. This is a picture from Tegmark. Some people have even asked, well, is it something to do with consciousness or life or just as complexity? Well, I take the view that really you can think of it as, it's better to think of it as being to do with complexity, because the whole point about the Big Bang is that as you go through the history of the Big Bang, which I briefly reviewed, you build up increasingly more complicated structures, so you get quarks and gluons and atoms, and then molecules and bar molecules and cells, and eventually at the top you end up presumably with brains and consciousness. But the point is, this development occurs during the Big Bang only because of all these fine-tunings I talked about. Now, to me, the precise selection criteria may not be crucial, because in some sense this pyramid of complexity may inevitably culminate in mind once the process starts. So I prefer to think of this as a complexity principle. But then, of course, in my last few minutes, I have to address the question of what is the explanation of the fine-tunings? And broadly speaking, there are different types of explanations. The most popular one now among physicists is the multiverse, the idea that there are many universes which have different values of the constants. Another sort of less popular view is that maybe it's something to do with consciousness, because some people think consciousness collapses the wave function, and therefore maybe the universe evolves into human beings who look back and contemplate the being of the universe like we're doing now, and maybe in some sense that brings the universe into existence. And then, of course, you can adopt a more theological view and say, well, maybe God just chose all the constants so that we can be here. Now, I'm not addressing theologians here, but I know there's one eminent theologian in the audience who has written a book on this very topic. But anyway, the point I want to make is that really these explanations come under different categories. I mean, the first is physics, the second is metaphysics, the third is theology. By and large, as you can imagine, most physicists would prefer a multiverse. And that doesn't mean that's the correct explanation. From a logical point of view, all of them might be correct. But from a physicist's perspective, it's the multiverse which is most popular, so that's the one I'm emphasizing in my talk. But I should also warn you that other people think the multiverse is also rather metaphysical. I mean, George Ellis is in the audience. And so they should shift everything along a bit, and for them the only physical model will be something like the universe which creates itself. So this is Hawking's picture of the universe in a nutshell. So you don't need... Some people think that the multiverse is just as metaphysical as God, and so they would like that. And all I would say in response to that is that it's an arguable point. I would stress that in some sense the border between physics and metaphysics is always fuzzy. So this border in some sense historically has evolved. So what was the metaphysics yesterday may be physics today, and what's metaphysics today may be physics tomorrow. And I just want to say that obviously my own view is I favor the anthropic picture, the multiverse interpretation. This was the book which I'm afraid I can't help advertise, Universe or Multiverse. The point about the multiverse is that if you believe there's a multiverse where the constants are different, then in some sense the fine tunings, the strong, what I call the strong tunings, become a natural aspect of the weak anthropic principle, because you're just saying we have to be in one of the universes which does actually exist. And in some sense, after all, the aim of physics is to try and explain what happened at the Big Bang and not just put it into the hands of the theologians. But if you have a physical theory for how our universe arose, it's not surprising that you have a model for other universes, other Big Bangs as well. And the fundamental issue is this is a famous diagram from Martin Rees. Is the fundamental theory of physics going to explain the constants uniquely, in which case there is no role for anthropic reasoning, or will it allow universes which have different values of these parameters, different cosmological parameters, etc.? If that's the case, then there is, of course, scope for anthropic reasoning. And my view is that the multiverse would naturally explain the fine-tuning. So here's my favorite picture of Einstein. What really interests me is whether God had any choice in the creation of the world. Now, can I just go one more minute because of the 1 minute silence? So I'm going to have 1 minute non-silence, if that's all right. Because I'm not going to go through all of the multiverse scenarios, but I just want to stress that the multiverse scenarios come from a combination of cosmology and particle physics. The multiverse wasn't created to explain the fine-tunings. It has come independently. And in cosmology, we have the cyclic model, eternal inflation, colliding brains. We have the quantum many worlds, we have string landscape, we have quantum cosmology. I had some pictures, but I'm not going to go through all of these. But the fundamental question is, what we do know is that something must lie beyond our cosmological horizon. And the question which eternal inflation raises is that, well, is our observable universe just a tiny part of a larger physical reality? So in this diagram, we're just one bubble, and we're part of one little bubble. Now, again, you can speculate, you can say that this is philosophy rather than physics, but at least that's what the claim is. And I'm just going to do this now very quickly. There's a string landscape, which I'm not going to talk about, but David Marsh is going to talk about that. There's the many worlds of Everett. There is quantum cosmology, and of course, Thomas Hertog is going to talk about that in much greater detail. There's brain cosmology. I'm not going to go through the objections to the anthropic principle. Well, I will quickly go through the objections and then finish. The first objection is that it's just all a coincidence, and you get different views on that in the book from Stenger and the paper by Luke Barnes. Whether it's a coincidence just depends on how many there are and how fine they are. I don't think it's a coincidence. I think there really is something fishy going on. It's argued that the fine-tunings are post hoc. Triple alpha and lambda were predictions. It's argued that it's too anthropocentric. It all assumes carbon-based life, for example. I mean, I agree, but to me, that's why I like to emphasize the complexity principle. They don't, of course, explain exact values of the constants, but then that's what you expect in the multiverse picture. You would prefer a final theory to predict the constants uniquely, but in that case, and then the tunings would arise, but in that case, it's an amazing coincidence that the values predicted are exactly what is required for life. And I just want to end by flipping to the, sorry, I'm getting this, you can't read this, this is subliminal. I just want to end with the final quotes from my book, actually. Frank Wilczek. The previous gathering had a defensive air. It prominently featured a number of physicists who subsisted on the fringes, voices in the wilderness who had for many years promoted strange arguments about conspiracy among fundamental constants and alternative universes. Their concerns and approaches seemed totally alien to the consensus vanguard of theoretical physics, which was busy successfully constructing a unique and mathematically perfect universe. Now, which is 2005, the vanguard has marched off to join the prophets in the wilderness, and another Nobel laureate, Steven Weinberg, we usually mark advances in the history of science by what we learn about nature, but at certain critical moments, the most important thing is what we discover about science itself. These discoveries lead to changes in how we score our work in what we consider to be an acceptable theory. And I will end at that point. Thank you.
Thank you, Bernard, for this very nice introductory talk, and we have time for a couple of questions.
It's just to have a second glimpse of the Higgs slide.
Yes, I will go back to that while the others are asking a question. That's okay, I'll go back, but I can do that and answer another question at the same time.
Other questions?
Hi there. A general question on order and disorder.
Yes.
And how it relates to what you're saying. We have a nice ordered brain to do all these processes, but the root of the universe is to increasing disorder, even where, say, you have spiral structure growing, but at the expense of increasing velocity dispersion, just to look at a galaxy. How does that link in with all your...
It's true that in the second law of thermodynamics says that globally disorder always has to increase. But the point is that you can always have local pockets of order building up. There's always the disorder outside, so a lot of our life on Earth depends upon the sun, but of course most of the energy of the sun is in radiation, which is increasing the energy of the universe. And that's why, in some sense, the pyramid of the complexity is a pyramid, because as you get to more and more complex things, like brains, it's a smaller fraction of the universe which is involved in them. So there's no contradiction there. But one of the great advances of chaos theory and complexity theory is the realization that despite the law of thermodynamics, you can actually expect the buildup of order. But the point I was making is that it only happens if you have these fine tunings. It wouldn't happen for any universe.
So I have a question about,
Yes,
so suppose you have a non-anthropic explanation and an anthropic explanation.
Yes.
So the question is, how would you decide between the two? A related question is, how would you falsify an anthropic explanation? Is there a way of saying this is wrong, given that there is a way to say it's right?
I mean, I would it sounds a bit hypocritical. I would always favor the non-anthropic principle if it was there, okay, first of all. And I can't say for sure that there won't one day be a non-anthropic explanation for some of these things. But really it relates to the last point, which I said, even if there is a final theory which explains these coincidences, it still becomes mysterious that that final theory happens to predict the coincidences which is required for life. I mean, when you say, how can you disprove it? I mean, to me, the two ideas now are very much linked with the multiverse, because to me, the multiverse is what gives some justification, because to me, at least, that's a possible physical in inverted commas explanation for the fine tunings. But then the question is, well, can you verify or disprove the multiverse? And that's the sort of question George always asks. And of course, I would like to think you could, but the answer might be that you can't. In that case, you really are in exactly the sort of problem George is talking about. So, I mean, for me, a lot is going to depend upon whether we're somehow going to get some evidence, independent evidence for the multiverse. But in the meantime, I see the fine-tunings as sort of indirect evidence for the multiverse, because I can't think of anything else. But I know you are going to give a talk later in the day which may have a different view, so I'm looking forward to that.
Bernard, the question of evidence is one thing, but you had your slide about what it explains, and the multiverse does not explain the ultimate issue. It simply shifts it up one level. Because the question, why is the multiverse fine-tuned for life? Because the multiverse, you had your universe generating machine, that has got constants in it. Those constants, some values of those constants will create universes which allow life and some won't. So all you've done is shift it up one level.
Well, it's true. I mean, it's like saying, you don't need God to make the universe, but you could need God to make the multiverse. So I agree in a certain sense, you're shifting it up one level, but that's what physics does. It's often shifting explanations up one level, and reductionist physics sort of claims you're getting, I don't know, up or down a level. In that sense, because of course you haven't ultimately explained the multiverse either. So in some sense I agree with you, but all I'm saying is the nature of physics is that it does shift things up a level, and some people think shifting things up a level is progress.
Okay, so I'm afraid we have to shift this discussion for the discussion session at the end of the morning.